Hey folks, welcome to my channel Number Pen. So in this video, we're going to look at the product rule in differentiation, right? So there we have the product rule written for us on the screen. If u and v are two differentiable functions, then d by dx of uv equals v du by dx plus u dv by dx, right? So remember folks, u and v are differentiable functions and they are dependent on the independent variable x, right, in all these rules. So again, we're going to try and prove this using first principles, right? And what is our first principle state? Before that, let's represent our uv as f of x, right? So if my uv is f of x, it actually means u of x into v of x, right? So what is my f dashed of x, right? So your d by dx of uv is nothing but your f dashed of x, right? And my f dashed of x is written like this, right? And so my f dashed of x is written like this, right? So my d by dx of uv is equal to f dashed of x. Why is that? Because my f of x is equal to u of x into v of x, right? So I can further use first principles and write the definition for f dashed of x, right? And my f dashed of x, when I write it as per the definition of my first principles, what do I get? My f dashed of x is equal to limit h tending to 0, and I have my f of x plus h in the numerator minus of f of x divided by h, right? And what is my f of x plus h? Right? My f of x plus h is nothing but when my f of x equals u of x into v of x, then my f of x plus h is nothing but u of x plus h into v of x plus h, right? And my f of x, we know that it is equal to u of x into v of x, right? And I still have my h in the denominator. So now, what is it that we can do, right? I'm going to move to the next line. And all that I'm going to do is let's try this out and let's see if it works. U of x plus h dot v of x. And then again, I subtract it by the same expression because it doesn't change my way, right? So what is it that I've done? I've added this new expression and I'm going to highlight this in yellow here. And what is that expression all about? Expression is u of x plus h into v of x, right? Minus u of x plus h into v of x, right? So it doesn't change the expression. All that I've done is added and subtracted the numerator by the same expression, right? Which is my u of x plus h into v of x. Now it looks like I can use this to combine this expression, which is u of x plus h into v of x plus h, and I'm going to combine this with u of x plus h into v of x. So I'm highlighting it in green again. And I can combine my u of x plus h into v of x, which is highlighted in yellow out here, with my u of x into v of x, right? So So in the next step, all that I'm going to do is rearrange this. So this is what we get, right? And so on the green portion, I can pull out my u of x plus h, right? So I'm going to pull out my u of x plus h and rearrange this particular expression, right? So if I pull out my u of x plus h, what will I get? I will have my v of x plus h still. Remember, folks, we're still in the green part of the expression. And then I have my v of x, right? I close my flower bracket, and then I have my h. And then I move to the yellow part. I'm going to separate this, folks, right now. I have another common factor, which is v of x, right? So again, I pull out my v of x, right? Open my flower bracket, and then I have my u of x plus h minus u of x. Close my flower bracket, and then I have my h, right? So this entire green expression, we have a common factor, which is u of x plus h. I pull that out and rewrite the expression, and the entire yellow portion, I have a v of x as a common factor. So we pull that out and rewrite this expression, right? Now I know that my u and v are differentiable functions, right? So, and if you go back and look at some of my previous videos, I would have talked about differentiability implying continuity, right? So a continuous function need not necessarily be differentiable. But if a function is differentiable, and that's what is the assumption here, we know that the function is definitely continuous, right? So in all these u of x and v of x, which we're talking about, both these functions are actually continuous, right? And I'm going to draw your attention to the algebra rule of continuity, right? So if u of x is continuous, right, what is my u of x plus h, right? Let me highlight it by a different color. Maybe I'll call it by turquoise. My u of x plus h, limit h tending to 0, is nothing but u of x, right? And why is that? Because this particular function u of x is differentiable, and therefore it is continuous as well, right? And when it is continuous, I know that my limit h tending to 0, u of x plus h equals u of x, right? And that's the basic condition for continuity, right? So I can rewrite this expression further, and I think more or less we have arrived at what we want to prove, right? So let me expand this again. 0. And because my u of x plus u of x is continuous, I'm going to write my u of x plus h as u of x, right? And then if I combine this, right, v of x plus h minus v of x, right, I can open my, what should I call this, big bracket? Yeah. And similarly, I have plus limit tending to 0, my v of x I've already pulled out, and then I open my big flower bracket. So my u of x plus h becomes equal u of x because u is a differentiable function, and that's an assumption. Otherwise, these rules don't apply. And since it is a differentiable function, it also means it is a continuous function. So my u of x plus h equals u of x, right? And folks, u of x and v of x are now independent of h, right? Which is, let me use, say, a blue color. The u of x and v of x now are independent of h, right? And the expressions which are highlighted in green and yellow are dependent on h. So we can rewrite this expression as u of x into limit h tending to 0, and have this expression. And similarly, I have b of x into limit h tending to 0. I have u of x plus h minus u of x divided by h, right? So that's how we rearrange this particular expression, right? Now I think we know what we will have to do, right? And what is this expression? The one in green along with the limits is nothing but my v dashed of x, right? And what is my v dashed of x? My v dashed of x is nothing but d by dx of v of x, right? So d by dx of v of x is nothing but dv by dx, right? So, and what is the second part, which is the yellow part of the whole expression? Limit h tending to 0, u of x plus h minus u of x divided by h is nothing but my u dashed of x, which is written as d by dx of u of x, which is du by dx, right? U and v, you do not necessarily have to, uh, you know, call out x all the time. It is basically an assumption that my u and v are functions which are dependent on the independent variable x, right? And you might wonder, why am I using this word independent variable x, right? When we discuss composite theorem in differentiation, we will look at that particular thing as well. So that's how we arrive at the proof for the product rule in differentiation. So d by dx of uv equals u dv by dx plus v du by dx. And we're going to see a lot of problems using the product rule in differentiation in our upcoming videos. So thank you. I hope you found this content useful. Please do subscribe to my channel and support. Thank you.